This is the notes on equilibrium. In Chem 1, we talk about how when equilibrium is reached in a reaction, there is no longer any observable change. This is where the reactant and the product concentration remains constant. However, this does not mean that there is no molecular activity. Reactants are constantly bouncing into each other to form products, and products are constantly bouncing into each other to form reactants. It also doesn't mean that there's a 50-50 split between reactants and products. That equilibrium, that balance, can be reached whenever the rate of the forward and the reverse reaction are the same. An analogy I like to bring up when discussing equilibrium is, instead of the really cold day that we have today, what if we were to go to Hawaii on a class field trip? And in doing so, we went to the beach. Whenever you go to a beach, there are people laying on the sand and there's people playing about in the water. It doesn't mean that there's the same amount of people both in the water and on the sand, but at some point there's kind of a balance reached, because if a whole bunch of people from the beach decide to go into the water all at once, the water's starting to get a little crowded. Some of the people are going to leave the water to go back onto the beach. On the other hand, if a whole bunch of people left the water to go onto the beach is starting to get crowded. Some of the people will go back into the water then. So you have this constant back and forth until there's a good balance that's reached. Really, in Chem 1, we needed you to know about this forward and reverse reaction aspect of equilibrium, this balance that can be reached. We also talked about Le Chatelier's principle. That's a topic that we will cover next class. Instead, today, we need to get into two other components of equilibrium. One is, unfortunately, just vocabulary. So when you look at WebAssign, there might be questions asking, what type of equilibrium is this? Well, if there's a chemical change or a chemical reaction occurring, we would refer to as chemical equilibrium. In Chem 1 right now, we are talking about states of matter. And at 0 degrees Celsius, ice and liquid water, or solid and liquid water, both exist. They are at equilibrium with one another. So physical equilibrium would be referring to a state of matter. Homogeneous is when all of the components of the equilibrium system are in the same phase. Heterogeneous is when there's more than one phase. That vocabulary is not, essential, but it is something that our textbook did bring up that we should be aware of. More importantly in this class is we are going to be getting into the mathematics quite a bit the rest of this semester with equilibrium. If I give you the generic equilibrium equation, where the capital letters stand for whatever compound or particle it is, the lowercase letters are the stoichiometric coefficients, here is a general equilibrium reaction. We know it's equilibrium by the fact that there is a double arrow. So A and B will make C and D. The equilibrium expression, if we are referring to the concentration of these, so if we have the molarity of these things, it would be the concentration of C raised to its stoichiometric coefficient times the concentration of D raised to its stoichiometric coefficient divided by the reactants to their stoichiometric coefficient. This K value is what's referred to as an equilibrium constant. Those of you who did the reading guide last time would notice that a K value that is greater than 1 means there's more products, or it's product favored versus reactant favored. A K value that's much less than 1 means it only makes a little bit of products. Mathematically, this should make sense. If we are taking products over reactants, if there's bigger amount of products at equilibrium, because we're looking at the concentration at equilibrium of these things, if there's more products, it would make sense that a big number divided by small would give you a big number. When we deal with acid-base chemistry next unit, you're going to be seeing small K values, like 10 to the negative 8th, for example. Not only can equilibrium be dealing with concentration, it can also be dealing with pressure. So equilibrium constant dealing with pressure would be the pressure of the reactants, the pressure of the products raised to their coefficient divided by the pressure of the reactants raised to their coefficient. There is a way to convert between equilibrium for pressure and equilibrium for concentration. Quite frankly, I'm only showing you this because it is in our textbook, but this is one of the equations that is no longer really required within AP Chemistry. So I'm not too concerned if you actually know how to use this. By the way, delta N just means the change in the number of moles from start to finish. So what's more important to you is knowing that equilibrium constants are products over reactants. That's the thing that you need to know. When we're doing the concentration of products over reactants, we do not have to worry about a pure solid or a pure liquid. Pure solids and pure liquids do not have a concentration. Think about it. Can you change how much water is in water? It doesn't really make sense. You can't dilute water, just like you can't water down a pure solid, because once you add water, you make it a solution. So in other words, when we are doing our equilibrium math of products over reactants at equilibrium, the only thing we should have to worry about is aqueous solutions, because those definitely vary in concentration, and gases not only vary in pressure, the last slide going over pressure of products over pressure of reactants, but gases, since they could fill different volumes, technically can have different concentrations as well. Next, the textbook goes over two-step reactions. This ties in nicely with kinetics because remember, two reactants can make products, but then those products can react to make the final reactants. The final products. So really, C and D are intermediates in this particular reaction. It's A and B making E plus F. But you could see a whole slew of a part A, a part B, a part C type test questions dealing with rate determining step, identify the intermediates. Well, each of these side reactions could have equilibrium constants. If the overall reaction is A plus B makes E plus F, because when you add these two reactions together, these cancel out, we could find the overall K value by multiplying the K value of this reaction times the K value of this reaction. Unusual thing about K values. K value is defined as the products over the reactants raised to their stoichiometric coefficients. Some students get confused about this because this is an equilibrium reaction, meaning it can go forward and reverse. For the purposes of equilibrium math, anything that's on the right-hand side of the arrow is considered a product, regardless of if there's more of it or less of it. Anything on this side is considered a reactant. So if I'm giving this reaction here, it would have a K value that I could calculate based upon the concentration of the products over the reactants. If I was given the opposite reaction, C plus D makes A plus B, I would have to flip this around, products over reactants. Or I could take that 1K value and just do the inverse function of it. The first day of WebAssign is having you manipulate K values. This is one of the ways that we can manipulate K values. Another way we could, here's our original reaction, but what if I had 0.5 in front of all these? So if I have half or 1/2 as the coefficient, when I do products over reactants, I'm taking them to the 1/2 power. Well, if everything's being taken to the 1/2 power, I could just take the square root of that original K value and get the K prime, the new K, for this reaction here. Typically what I've seen is this type of, here's the K for one reaction, now solve it for a very similar reaction, be it the reverse reaction like I've shown in the third bullet point, or change the coefficient like I did for the fifth bullet point. That's something that pops up more in the multiple choice aspect of equilibrium math. What you are going to be learning to do for the good portion of this year is what's called an ICE table. ICE stands for initial, the change, and equilibrium. For example, if I gave you a reaction where you started with both nitrogen dioxide and N2O4, so I gave you the initial amount of it, and let's say I knew at equilibrium there was 0.1 of the NO2 remaining. In order to solve for equilibrium, K, I need to know the concentration of everything at equilibrium to begin with. So I need to solve for this question mark right here. So to finish notes, I want to show you how to solve this particular reaction. Again, my general equation is the nitrogen dioxide making the dinitrogen tetraoxide. If the equation tells me to begin with, initially I have 0.5 molar of this, 0.05 molar of that. Change is something we're going to try to figure out. At equilibrium is 0.1 molar. Hopefully it's easy to see that I must have lost 0.4 molar of the NO2. Because if my initial concentration is 0.5, my ending is 0.1, that's how much I lost there. For every 0.4 molar of NO2, there's 1 N2O4 for every 2 NO2. Little stoichiometry. If this lost negative 0.4, this must gain 0.2. If I add my initial plus my change, it will tell me how much do I have at equilibrium. 0.25. Equilibrium math can be done when you know at equilibrium the concentration of the products and the reactants. If I first set up my expression, I'm going to have the concentration of N2O4, my products, divided by the concentration of NO2 squared. You need to raise it to its stoichiometric coefficient. If I then plug in the values I have circled above, 0.25 divided by 0.1 squared would equal an equilibrium constant of 25. Equilibrium constants are unitless. It also means at equilibrium there are going to be more products present than reactants present. This concludes the audio notes of equilibrium on the first 12 or so pages of the book. Next you should be doing some practice problems that are listed on the board before we move on from there into reaction direction.